Very good afternoon to one and all. Myself, Vinit Kumar, research scholar under the supervision of Yogendra Prajapati. I'm in IIT Allahabad. My presentation topic is Tunable Plasmonic Refractive Index Sensor based on the enhanced photonic spin Hall effect. This one is the outline of my presentation. This one is the outline of my presentation. Uh, Tunable plasmonic sensor, photonic spin Hall effect, motivations, objective method, and structure description, and what exact tunability in plasma proposed sensor, a result discussion and conclusion and inferences. First, come to the tunability portion. Tunable plasmonic sensor represent and the cutting edge technology in the field of the sensing and detection. And plasmonic involves the uh, interaction between interaction of the electromagnetic field oscillation, and is known as the surface plasmon resonance. Basically, surface plasmon resonance occur between the metal and dielectric layer. The resonance condition is the resonance condition is sensitive to change in the local environment, making it an excellent performance in the sensing application. This is a schematic diagram of my uh, paper. Come to the next. In the next context, a sensor. The tunability of the plasmonic sensor arises from the ability to adjust the resonance condition by modifying the property of the matter or the surrounding medium. And this can be achieved through the external factor such as the change in the temperature, refractive index, or other depending on application. Mm. Tunable plasmonic sensor can operate based on the various sensing in a mechanism like refractive index sensing and localized surface plasmon resonance. In our case, we are obtaining the resonance refractive index sensing. Next is the photonic spin Hall effect. Basically, photonic spin Hall effect is a phenomena in optics that mirror the spin Hall effect observed in the considered matter physics. It involves the manipulation and control of the spin angular momentum of light as it propagates through the medium. The photonic spin Hall effect is a result of the interaction between the spectral distribution of light polarization and refractive index variation in the medium. Basically, three terms is very important in the photonic spin alpha. First one is the spin angular momentum of light, and second one is the reflection and spin orbital coupling, and third one is the transverse shift of spin state. Basically, here we find here the splitting between the right hand polarization and left hand polarization. Uh, Polarization dependent Hall effect is the light of light. It known as the photonic spin Hall effect. Basic cause of the photonic spin Hall effect is the interaction of the spin and orbitals. And after this cause, the response is coming out the left and right circular polarized component of the light beam shifted transversely perpendicular to the gradient of the refractive index. This interaction also affects the trajectory and polarization of the light beam as it travels through the inhomogeneous medium. Basically, it is the optical version of spin Hall effect. And then come to my paper or the motivation. Basically, here we are using the graphene. Graphene has the capability to support the sulfur plasmon wave at a very low Fermi energy level, while owning its negative imaginary part of conductivity, a large confinement loss, and have a long propagation distance. Hence, these properties are very useful in the sensing application. Objective is to, by using this polarization gradient, improve the photonic spin Hall effect in the graphene assessed plasmonic refractive index sensor. Method here we are using the change in the optical change in the optical conductivity, and other one is the transfer matrix method. This is the schematic diagram of uh, my presentation. In this, there are three layers we are using. Uh, yes. Structural description. First of all, we are using a prism for coupling the light, which refractive index is 1.7231, and then we are coating in on a prism is a silver coating, and the coating thickness is about 46 nanometer. And other one is, then after silver is used as a plasmonic material. After the plasmonic material, we use a silicon for the field enhancement. The refractive index of the silicon is the 3.922. And after then we are using the graphene as the refractive index of the graphene is the calculated by the chemical potential. Graphene has a negative imaginary part of the conductivity. It has a frequency range. And the frequency range in graphene has a complex value which consists of the interval and conductivity. In this paper, we are considering three structures. In the first structure, we are using the substrate, after then the cell plasmonic layer, and the second structure, substrate, plasmonic layer, and cell field enhancement layer, and the third structure, we are using the graphene, and finding the sensitivity, detection accuracy, and the limit of detection. The method used here, uh, here is changing in the interband and interband and conductivity by the changing the chemical potential. This is the matrix. And other one method is use the transfer matrix method. Basically, transfer matrix method is the find out the reflectance and transmittance in the multiple layers. Come to the tunability in proposed sensor. In terms of the tunability, graphene's Fermi energy level is thought to be customized by the chemical doping, which result in the variation of the interband transmission and the modify in the imaginary portion of the graphene refractive index. This is referred to the Pauli's blocking in the chemical potential of the graphene influenced by the photonic spin Hall effect and sensor performance is uh, spin dependent splitting of the graphene based structure vary with the chemical potential variation. The chemical sustain impact the spin dependent and shifting. Graphene conductivity has a significant shift due to the large imaginary uh, compound of the big ratio of RS and RP, where RS and RP is the Fresnel reflection coefficient in the S in the case of the S polarization and P polarization. These are the result. In this study, we first of all we optimize the plasmonic layer, silver layer, that is 46 nanometer, and then we find the spin dependent, conventional spin dependent splitting, which is found as a near about 16 micrometer. After that, we coat the fill enhancement layer, uh, that is silicon. Silicon is optimized. Optimized silicon thickness is 13 nanometer, and then we find the RS and RP, and the ratio and the peak of conventional spin dependent splitting is goes to 52 near about 52 micrometer, and then we vary the chemical potential. After varying the chemical potential, I'll, applying the graphene in the spin dependent, and then splitting is goes to near about 1 to 1.5 at the chemical potential 1.9 1939, and then we obtain the sensitivity, figure of merit, and limit of detection, and by varying the refractive index from 1 to 1.1, and the chemical potential varies from the 0 to 1.2. This is the comparative result in the these three structures. Uh, First one is the sensitivity, second one is the figure of merit, and other one is the limit of detection. Uh, we see that in the first structure, second structure, and third structure, our sensitivity goes to 1262 25158. It is a very big change in sensitivity. Also in the figure of merit, also change from the 4337 to 23851, and the limit of detection is goes to 10 to, order of 10 to the power 7 to 10 to the power 8, minus 10 to the power 7 to minus 10 to the power 8. Uh, and the conclusion portion, in this research, we examined the graphenesis photonic spin Hall effect structural tunability. Change in the chemical potential may drastically modify the spin-dependent splitting of the light in photonics. That is goes to 1.15 micrometer. The magnitude of the conventional spin dependence if as obtained in far larger than the previously reported value. Would the refractive index of the sensing medium has an effect on the conventional spin dependence if making the suggest structure as a unknown sensing structure. The simulation revealed that either silicon or graphene in layer significant change transfer lead to the significant conventional spin dependence. SIF tunability also provide a graphene anisotropy. An optical refractive index sensor is early harmful as gas detection gas detection applications. And these are the references. Thank you.